In this video, we are going to explain and derive the four Maxwell's equations. Maxwell's equation number 1, also known as Gauss's law for electrostatics. Let us assume a closed surface filled with electrical charges. The surface can be imaginary, by the way. If the total charge is Q, then Q coulombs of electric flux will pass through the enclosing surface. At any point P, consider an incremental element of surface delta S and let the flux density vector ds make an angle theta with delta S. The flux crossing delta S is then the product of the normal component of ds and delta S. Thus, delta phi, which is equal to the flux crossing delta S, will be equal to the normal component of ds times delta S, which is equal to magnitude of ds cosine theta times delta S. In vector notation, this is equal to the vector dot product of ds and delta S. The total flux passing through the closed surface is obtained by adding the differential contributions crossing each surface element delta S. Thus, phi, which is the total flux, will be the integral of d phi, which is equal to the closed surface integral of d dot ds. The subscript s in ds denotes that we are measuring the flux density at the surface. If it's a trivial assumption, one can skip the subscript and just write d instead. Anyway, this integral is equal to the charge enclosed by the surface. Thus, phi is equal to q. Just remember that this is by definition. Now, over a volume of charge distribution, if rho v is the charge density, which is of course a function of position and time possibly of course, then total charge enclosed in that volume, denoted by q, would be a volume integral of rho v with respect to the volume differential dv. Therefore, the Gauss's law becomes the closed surface integral of d with respect to the surface element equal to the volume integral of rho v with respect to the volume element. Here v is denoting that the integration is taking place over the volume of the surface enclosed by S. Thus, in differential notation, S is del v. Now, let us apply Gauss's divergence theorem, which states that the closed surface double integral of d with respect to the surface element is equal to the volume integral of the divergence of d with respect to the volume element. Now, once again, v is denoting that the integration is taking place over the volume of the surface enclosed by S. Thus, we have that the volume integral of the divergence of d is equal to the volume integral of the volumetric charge density rho v. But since this is an identity, we can say that the divergence of d is equal to the volume charge density rho v. This is Maxwell's first equation, also known as Gauss's law for electrostatics. Remember, this law is true for both static fields as well as time varying fields. Maxwell's equation number 2, also known as Gauss's law for magnetism. The idea is very similar to the first equation, but since the magnetic poles always exist in pairs, the total magnetic charge, if you want to call it so, enclosed by a surface would always be 0. This is because the number of north poles would be equal to the number of south poles. It is just like having equal number of positive and negative charges enclosed in the imaginary surface. So, if B is the magnetic flux density vector on a closed surface, then the closed surface integral of B will equal to the total magnetic charge enclosed by the surface, which is of course equal to 0. Thus, once again, by the application of the divergence theorem, we can say that the divergence of B will be 0 always. So this is Maxwell's second equation. Once again, this equation is valid for both static and dynamic fields. Maxwell's third equation, also known as Faraday's law of electromagnetic induction. The force felt by a charge Q in an electric field with intensity E is equal to Q times E. E does not have to be a constant, by the way. It can vary with respect to space and time. Now, if the charge is moved by a small distance dl, then the work done would be equal to QE dot dl. Dot is denoting a dot product. Now, if the charge is moved in a closed path, then the total work done in doing so would be equal to the closed path integral of QE dot dl. This is equal to 0 in an electrostatic field, since an electrostatic field is conservative in nature. So moving a charge in a closed path results into 0 work done. However, if the electric field has been generated by some other means, for example, by a time varying magnetic field, then the work done would be equal to Q times EMF. Here, the EMF is actually the potential difference generated by a non-conservative field. Magnetic field is a non-conservative field, and by having a time varying magnetic field, an electric field is generated, and the potential difference offered by that is called the electromotive force. So here, the closed path integral of QE dot dl will be equal to Q times the EMF. Notice that this integral is no longer 0 and the field as a whole is no longer conservative. Since we are assuming the charge to be constant, we can get rid of the charge Q from both sides of the equation, resulting into the closed loop integral of E dot dl equal to EMF. But Faraday-Lenz's law tells us that the EMF produced by a time-varying magnetic field is given by negative of del phi del t, where phi is the magnetic flux. Now, if B is the magnetic flux density vector at a point, the total magnetic flux in a surface would be phi equal to the surface integral of B dot ds. Therefore, the closed path integral of E dot dl will be equal to minus the partial derivative with respect to time of the surface integral of B dot ds, because it represents phi. Note that S here is not denoting a closed surface, and C is actually its boundary. So, in the notation of differentials, C is equal to del S. Now, let's remember Stokes' law. It tells us that the closed path integral of E dot dl is equal to the surface integral of the curl of E. Therefore, from Faraday's law, we can write that the surface integral of the curl of E is equal to negative partial derivative with respect to time of the surface integral of B dot ds. Since the right hand integral is happening with respect to the surface element, it is independent of time and the derivative can be brought inside the integral. And since the result is an identity, we can say that the curl of E is equal to minus del B del T. This is Maxwell's third equation, also known as Faraday's law of electromagnetic induction. Keep in mind that the curl of E would be 0 for an electrostatic field. But if there is a time varying magnetic field present, it will induce an EMF, and because of that, the result will be equal to minus del B del T. Now, before we can talk about Maxwell's fourth equation, we need to talk about the concept of the conservation of charge. That is, charge can neither be created nor be destroyed. Consider a volume V, and let's assume that I amount of current goes out of the volume. Then its charge density will go down. This current can be expressed as the closed surface integral of the current density, where once again S is equal to del V. It represents the boundary of the volume oriented by the outward pointing normals ds. J is the current density vector at the surface of the volume. J points in the direction of the current. Now, the total charge in the volume V is the integral of the charge density. So Q is the volume integral of rho V. Thus, the rate of change of charge inside the volume is the time derivative of Q. And as such, this is equal to the volume integral of the time derivative of the charge density. But since, because of the conservation of charge can neither be created nor be destroyed, the outgoing current I causes a negative change in the charge inside the volume. Thus, I will be equal to minus dq dt. Therefore, the surface integral of the current density will be equal to negative volume integral of the derivative of the charge density inside the volume. Once again, using the divergence theorem, we can write that the closed surface integral of the current density is equal to the volume integral of the divergence of the current density. And thus, the volume integral of the divergence of current density will be equal to negative volume integral of the rate of change of charge density with respect to time. And since, once again, this is an identity, we can write that the divergence of the current density will be equal to minus del rho V del T. This equation represents the conservation of charge. In general, this sort of equations are known as the continuity equations. Now let's talk about the Maxwell's fourth equation. This is also known as Ampere's law with Maxwell's corrections. Assume that the total current I passes through a closed path C. And then Ampere's law tells us that the closed path integral of the magnetic field intensity vector H with respect to the length element dl is equal to I, where I is the total current enclosed by the closed path C. Now, I can be represented as the surface integral of the current density J. So, the closed path integral of H will be equal to the surface integral of J. But by Stokes' law, we know that the closed path integral of H is equal to the surface integral of the curl of H, where C is equal to del S and C represents the closed boundary of the surface S. Therefore, Ampere's law becomes the surface integral of the curl of H equals to the surface integral of the current density. But since once again this is an identity, we can say that the curl of H is equal to the current density. This is true for non-time varying fields. But notice that if we calculate the divergence of J, it turns out to be 0. Since divergence of J would be equal to the divergence of the curl of the vector H. But as an identity, we know that the divergence of the curl of any vector is always 0. So in this regard, if this equation is true, then the divergence of J is always going to be equal to 0. But from the continuity equation, we know that the divergence of J is equal to minus del rho V del T. But since divergence of J is equal to 0, del rho V del T will also have to be equal to 0. So the equation that the curl of H is equal to J holds true only if there are no local variations of charges. To remove this unrealistic limitation, say we add an unknown term JD to the Ampere's law, such that the curl of H is equal to J plus JD. Now again, if we calculate the divergence on both sides, the left hand side becomes 0, and on the right hand side we have the divergence of J plus JD. This gives that the divergence of J will be equal to negative divergence of JD. But since the divergence of J equals minus del rho v del t from the continuity equation, we can say del rho v del t will be equal to the divergence of JD. But from Maxwell's equation number 1, we know that rho v is equal to the divergence of D. Therefore, the divergence of JD is equal to the time derivative of the divergence of D. Since the derivative with respect to time and space are independent, we can interchange the order. Thus, as an identity, we have JD equals to del D del T. Thus, the Ampere's law for time varying fields become curl of H equals to J plus del D del T. Here, J represents the current density due to the free charges. So, we often denote it with JF instead. And JD, which is equal to del D del T, is a current density like term, resulting due to bound charge variations. This is known as the displacement current density. So, in summary, these are the 4 Maxwell's equations, and these are the fundamental building blocks of electromagnetics.